sampling variability. What this refers to is the fact that different random samples of the same size from the same population will produce different estimates. So it refers to the fact that different random samples if you have your own car, you shouldn't be trick-or-treating. No, I'm a little concerned about that, Michael. Okay, different random samples from the same population, or I'm sorry, of the same size from the same population will produce different estimates. So let me give you an example on this. I'll give you a second to get caught up. So let's say I take everybody's test scores from the last Chapter 2-3 test, and I put them in a big pot, and I randomly select 10 of the test scores from all 125 kids that took the test or so. And I average those 10 scores. And then I take another 10 from the same pot, and I average those 10 scores. And then I take another 10 from the same pot, and I average those 10 scores. Would it be reasonable to think that all of those averages would be exactly the same? No. They're going to be different, hopefully not drastically different, right? But they're going to be different. And that's what this sampling variability speaks to, that there's going to be some difference there. So that's you hope that they're not greatly different, but they will be different. All right, and sample size. Sample size is important for a lot of reasons, but estimates from larger samples are more precise. Estimates from larger samples are more precise. What we mean by precise is they should more closely match the population. If a sample size is large or larger than another, there will be less spread. I think it's been since Chapter 1 that we sort of talked about that sort of thing, but when we look at a normal curve, if our sample size is fairly small and it's normal, then the curve is probably going to be pretty low and wide. What happens if I increase my sample size? The curve tightens up and gets taller, right? It narrows up and gets taller. So the spread changes with sample size. So far, so good. Everybody with me? All right. Statistically significant. This is a huge idea in stats, and usually, at least in previous years, we didn't get this introduced to us until second semester. I'm kind of glad that we get to dip our toes into it a little bit here. It'll come back in a big way later. But something that's statistically significant is when observed results of a study are too unusual to be obtained by chance. When observed results of a study are too unusual to be obtained by chance.
So, what about, sometimes the fact that it does happen? How would you do that? Like something that's just freakishly unusual and it is by chance.
Well, that does happen. And let me finish this up, and I think hopefully I can address that. Okay. Yeah, you're right. Sometimes an oddball thing hits. So to assess this, what we have to do as researchers is to assume the results of an experiment or study will be equal. Assume the likelihood of something to happen is as equal as the other thing, is basically what I'm getting at. What I mean by that is this. When they were looking at observational studies about smokers versus non-smokers, the assumption that the researchers have to take is that if you smoke or you don't smoke, your incidence of disease is equal. Okay? Now we know it's not because of studies, but the assumption is that it's equal. And then what you do is you look at the two results, and if the results are statistically significant, meaning that they're unlikely to be obtained by chance, then you can conclude that smoking, for example, causes a higher incidence of lung cancer. So the other thing I want you to add to this is the top or bottom 5%. And I think this will become clear when we look at a problem. We're going to look at a problem today that deals with this. We'll look at it together. It's pretty hard to get all the details of this down without, I think, looking at some sort of an example. But the example of the smoking would be that the incidence of lung cancer was so high among smokers that it couldn't possibly have been random chance that those people happened to get lung cancer. Does that make sense? So when we're looking for that sort of unlikely event to happen, is there a 5%? Are they on the top 5% or are they in the bottom 5%? This number can change, but we'll deal with that another time. But 5% is a good sort of direction here for now. All right, and we'll get back to that in the problem. Inference. I want to give you the definition of inference. The definition of inference is a conclusion reached on the basis of evidence and reasoning. A conclusion reached on the basis of evidence and reasoning. Inference. So we want to be able to make an inference about what we see statistically. That's a good thing. There are some guidelines. We call the guidelines the scope of inference. Everybody with me? Are we okay? Switch to the next page. Okay. All right. The scope of inference. There's two of them. Random selection of individuals allows inference about the population from which the individuals were chosen. Random selection of individuals
Individuals or subjects?
could be either. It could be either. Yeah. So whether you're selecting mice or people or trees or cars, you need randomness. Random selection of individuals allows inference about the population from which the individuals were chosen. So what that's saying is that if you design an experiment or a study well, and you use random selection, that allows you to actually make inference, make some sort of conclusion about the data that you see. The other one is random assignment of individuals to groups allows inference about cause and effect. Random assignment of individuals to groups and they say groups, what I'm thinking are blocks. Allows inference about cause and effect. We have to be cautious about cause and effect. We really do. I mean, think about the hot dogs and the lung cancer, right? We've got to be really careful about cause and effect. But if you're doing everything you right and you have random assignment of individuals, then you can make some comment about cause and effect. So let's say I want to look at 2 diet plans and I randomly select 150 people. Half of them do one diet, half of them do another diet. After I tabulate the data that I've gathered after some time, then I can make a comment about cause and effect, perhaps. Okay. All right, data ethics. This is the last bit. It's a little on the long side, and I apologize, but it won't be longer than the page. Data ethics. There are 3 of them, 3 main ethical points. All planned studies must be reviewed in advance by an institutional review board charged with protecting the safety and well-being of the subjects. If you can figure out a great way to shorten that up, feel free. All planned studies must be reviewed in advance by an institutional review board charged with protecting the safety and well-being of the subjects. Just to be clear, in this class, if we do any kind of like experiment or anything like that, I am the institutional review board. Okay? So we have done things like that in this class in the past. I'm not sure how I'm going to do the projects this time around. I'm hoping to do something a little bit different. But anything where you would be administering treatment or something like that, you've got to run that by me first. And I get to say yay or nay because I am the review board. All right. The next one, all subjects must give their informed consent before data are collected. All subjects must give their informed consent before data are collected. Yes.
Does this apply to like always have an opinion?
I think that might be implied. if you are like an exit poll or something like that, and people are standing outside and say, how did you vote? I think the consent would be implied probably in the answer more than anything else. But I might be wrong there. They might literally have to say, hey, we'd like to know how you voted. Would you agree to answering that question? Fair question that you ask. Since I've never done it, I don't know if an implied consent by giving the answer straight up would fly. Yeah, not sure on that. Okay, and lastly, last bit. All individual data must be kept confidential. Only statistical summaries for groups of subjects may be made public. All individual data must be kept confidential. Only statistical summaries for groups of subjects may be made public. Statistical survey would die without that. Could you imagine that you agree to be part of some statistical survey and you're reading in some magazine or something like that and it says, and in this survey, Bob Smith answered, right? And maybe the answer is particularly harmful. Maybe it was rather sensitive kind of thing. That could be a real problem. So individual data must be kept confidential. I don't know that we've been perfect about that in the past in this class, although probably we have been, I guess. So in the past what we've done is we've done questionnaires where students make a questionnaire that tries to be unbiased and a questionnaire that attempts to be biased. And we've gotten a few pretty interesting answers from some of the students that have taken those surveys. Now, we never ask for name or grade. Well, sometimes we ask for grade. We never ask for name or anything that would individually identify. But there have certainly been some times where we've gone, look what this guy or girl wrote. This is good stuff. This is funny, you know. But then that's also within the confines of the classroom or the researchers, not exposed to the public as well. So, all right. That's it for notes today.